Let your breath slow your shoulders drop, and for just a moment, allow the weight of the day to fall away like dust settling after a long journey. There's a star you can see from Earth, Alpha Centauri, shimmering just over 4 light years away, close enough to photograph, close enough to dream about. But tonight, we're going to discover why every scientist, every engineer, every machine we've built has quietly admitted the same truth: we may never set foot there. Not in our lifetimes, not in 1,000 lifetimes. Where are you right now as you hear this, curled up in bed, walking through evening streets, or watching the last light fade from your window? What small corner of the world holds you while we both gaze toward the same unreachable horizon? If you'd like to stay and wander this question with me, you're welcome here. Perhaps a gentle, like a quiet subscribe, or simply your company as we explore why the closest star might as well be forever away. Let's begin. There was a night in human history, no one remembers exactly which night, when someone, perhaps a child, tilted their head upward and asked the first question without an answer: those stars up there, can we reach them? Picture this: 40,000 years ago, a cave mouth opening onto darkness. Inside, fire crackles against stone. The tribe huddles close. Warmth is survival. But one figure sits apart, staring upward at points of light scattered across the void. For generations, humans had seen these lights, used them to track seasons, to navigate. But on this night, someone recognized something that changed everything. They weren't holes in a dome. They were places, actual locations in space. And if they were places, the question became inevitable: can we go there? This moment represents the most consequential cognitive leap in human history, the birth of something that hadn't existed before in 3 billion years of life on Earth, longing for the unreachable. Every other species lives within its niche. Lions hunt, birds migrate, all driven by instinct. No lion dreams of hunting on the moon. No bird wonders what lies beyond the horizon. But humans, we evolved to survive. And then a bug appeared. We developed the ability to imagine beyond our circumstances, to see not just what is, but what might be. This wasn't survival instinct. This was wonder. And wonder is dangerous. Once you can imagine beyond the horizon, you cannot stop imagining. The question becomes a splinter in the mind. The child by the fire feels something humans had never felt before: loneliness. Not the loneliness of being apart from the tribe, but the loneliness of recognizing that the universe contains beauty in places you cannot touch, that you can see forever, but reach only as far as your legs carry you. In feeling that ache, humanity took its first step toward the stars. Fast forward, around 190 BC, Greek astronomer Hipparchus calculated the moon's distance using parallax 384,000 kilometers, 10 times Earth's circumference. Then he tried the same technique with stars, observed from different positions, waited 6 months, measured the shift. The result? 0. No detectable parallax. The stars were so distant that Earth's entire orbit, 300 million kilometers across, became a point. Negligible. That 0 should have ended the dream. It didn't, because humans possess a stubbornness that defies mathematical proof. We looked at those measurements and thought, not yet, but someday. Perhaps we were born lonely, because the universe was born too vast. The Big Bang created distance, space expanding, carrying galaxies apart, ensuring most of the universe would spend eternity unable to touch. We are children of that expansion, atoms that achieved consciousness long enough to recognize our isolation and hate it. But knowing you want to reach something is one thing. Seeing exactly what you're reaching for is something else entirely. And the night we first saw Alpha Centauri clearly understood not just that it existed, but what it actually was. That was the night hope and despair were born as twins. Alpha Centauri isn't one star, it's a family. Stand outside on a clear night in the southern hemisphere. Look toward Centaurus. Find the third brightest point in the sky. That light seems singular. Point a telescope, and the truth reveals itself: two stars locked in embrace. Alpha Centauri, A and B, the eternal waltz. They orbit their common center of mass every 79.91 years, sometimes approaching as close as Saturn's distance from our Sun, sometimes drifting to Pluto's distance. But they never leave each other. Their masses have locked them into choreography, as inevitable as marriage. Alpha Centauri, A resembles our Sun, yellow, steady, warm, the kind of star that makes Earth-like planets possible. Alpha Centauri B is smaller, cooler, an orange star burning with half its companion's luminosity, the quiet partner providing balance. For nearly 5 billion years, they've circled each other. Through every event on a small blue world, 437 light years away, they've danced, unchanging, together. But every family has secrets. Proxima Centauri, the red exile, it sits 13,000 astronomical units away from the binary pair 0.21 light years, far enough that astronomers debated whether it even belonged. But it does. Proxima orbits the pair once every 550,000 years, a lonely ellipse through cold space, the estranged child who never quite fits. Proxima is a red dwarf, small only 12% the Sun's mass. Its surface glows dull red, radiating only 0.17% of solar luminosity. But what it lacks in size, it compensates in fury. Proxima erupts constantly. Stellar flares explode from its surface, briefly doubling its brightness, unleashing radiation storms that would sterilize planets. X-rays, ultraviolet firestorms, charged particles at near light speed. For 3 billion years, Proxima has raged alone, too far from its siblings to influence them, too bound by gravity to escape, a cosmic outcast, burning cold and angry in exile. Then in 2016, astronomers discovered something impossible. Proxima has a planet, Proxima b, orbiting in the habitable zone, rocky, potentially harboring liquid water, possibly impossibly a home. The discovery electrified humanity. We have a neighbor, not a statistical possibility in some distant galaxy, but an actual neighbor, a specific world orbiting a specific star where life might exist, 4.24 light years away, the closest possible destination. But Proxima b is no paradise. The planet orbits every 11.2 days, circling at just 7.5 million kilometers. At that proximity, gravity has locked the planet's rotation. Tidal, locked. Forever. One hemisphere faces the red star eternally. The other faces endless void. Imagine standing on the day side. The sky glows deep crimson, not blue like Earth's, but blood red, rust red. Proxima hangs motionless overhead, a dull red eye that never rises, never sets. The ground might reach hundreds of degrees. Water boils away. Atmosphere burns. Walk toward the night side. Temperature plummets. Red glow fades. Absolute darkness closes in. Here, ice stretches kilometers thick. All the planet's water frozen over billions of years. Between these extremes lies a narrow band, the Terminator, the twilight zone where eternal day meets eternal night. Here temperatures might remain moderate. Here, if anywhere, life could exist. Huddled in permanent dusk, adapting to a sun that never moves. And if you look up from that twilight zone, if you scan the crimson sky, you see them. 2 points of light, brilliant white against the red, close together like paired pearls. Alpha Centauri, A and B, the distant family, the binary stars shining across 0.21 light years of void. From Proxima B, they appear as bright as Venus from Earth, close enough to see clearly, far enough to remain forever beyond reach. A reminder that even in a family of stars, some members exist in exile, close enough to witness the gathering, too far to ever attend. The sky on Proxima B would break your heart. That crimson expanse with 2 white pearls embedded in it, a constant reminder of proximity and distance of belonging and isolation of family, just out of reach. The metaphor cuts deep. Proxima is us, humans staring at distant lights, aching with the knowledge that we can see but not touch, that we exist in the universe but remain fundamentally alone. If you lived on Proxima B, how would you look toward Earth? Would you see our sun, a distant yellow point in that red sky? Would you feel the same longing, the same impossible desire to cross the void? When telescopes confirmed Proxima B in 2016, humanity held its breath. We have a neighbor, an actual neighbor, right next door. The number felt manageable, 4.24 light years. That translates to 40 trillion kilometers. Drive a car at highway speed, non-stop 45 million years. Fly on a commercial airliner 12 million years. The fastest spacecraft we've built, 6,300 years. But we heard 4.24 light years and thought nearest star, closest destination, maybe reachable. The number deceived us, made the impossible sound merely difficult, made us believe that with enough ingenuity, we might cross that gulf. 4.24 light years. It sounds so close, but that's because we don't understand what light years actually mean. We don't comprehend what light is. We throw around 300,000 kilometers per second without grasping the violence it represents. The absolute speed limit, the cosmic barrier. 4.24 light years sounds close, but it's only close because we haven't truly understood what light is and what distance means when you're trying to chase it. And that's when we realize perhaps the greatest barrier isn't distance, it's time. Light is the fastest thing in the universe, but it always arrives late. We call it the speed of light, as if speed were its defining characteristic. But that misses the point entirely. Light doesn't move fast. Light moves at the cosmic speed limit of loneliness, 300,000 kilometers per second. In one heartbeat, it circles Earth 7 times. In 1.3 seconds, it reaches the moon. In 8 minutes, the sun. But Alpha Centauri, 424 years. Every photon that touches your eye tonight from that distant star began its journey in 2021, before this moment existed, before whatever happened to you last week, before the person you were yesterday became the person you are now. When you look at Alpha Centauri, you're not seeing it as it is. You're watching a postcard from the past, a message that left 4 years ago, traveling at the universe's maximum velocity and still arriving late. This is the paradox of observation. We never see the universe's now, only its history, layered by distance. The sun you saw rise this morning, 8 minutes old. That light had already departed before you opened your eyes. You've never seen the sun as it is, only as it was delayed by the time it takes light to cross 150 million kilometers. Andromeda Galaxy, that faint smudge in autumn skies, 2.5 million years old. When those photons left, humans were still learning to chip stone. Homo erectus walked African savannas, completely unaware that their light would one day reach a species that didn't yet exist, looking up from a planet they would never imagine. Even your reflection in the mirror is 1 nanosecond old. Light bounces from your face, crosses the gap, enters your eye. The delay is imperceptible but real. You have never seen yourself as you are, only as you were a fraction of a moment ago. Everything you perceive is archaeology. Every observation a fossil, every image a memory. The universe doesn't allow presence, only echoes. What this means for travel is devastating. Even if by some miracle of engineering we don't possess, we could travel. At the speed of light, the journey to Alpha Centauri would take 4.24 years. One way, no communication with home during transit, no course corrections, no abort button. 4 years, 2 months, 28 days of absolute commitment. But we can't travel at light speed. Nothing with mass can. Einstein's relativity draws a hard line. As you accelerate toward light speed, you grow heavier. Not metaphorically, actually heavier. The faster you go, the more energy required to go faster still. At light speed, your mass becomes infinite. The energy required becomes infinite. The universe doesn't forbid faster than light travel. It just makes it cost more than exists. So, let's look at what we actually have. Voyager 1 launched September 5th, 1977, 48 years ago. Humanity's most distant ambassador. Currently 24 billion kilometers from Earth. So far that radio signals take 22 hours to arrive. The edge of everything we've touched. It has crossed the heliopause, the boundary where the sun's solar wind surrenders to interstellar space. It is, by definition, the first human-made object to enter the region between stars. How far has it traveled toward Alpha Centauri? 0.02 light years. After half a century of continuous flight through perfect vacuum, moving faster than any spacecraft we've ever built, Voyager 1 has covered 2/1000ths of 1 light year. At its current speed, 17 kilometers per second, 200 kilometers per hour, Voyager 1 would need 75,000 years to reach Alpha Centauri. 75,000 years. Modern humans have existed for 300,000 years. Written language for 5,000. The oldest continuous civilization is 4,000 years old. The pyramids were built 4,500 years ago. If Voyager 1 were a person, it would witness 3,000 generations born, live, grow old, and die before reaching the destination. Entire languages would evolve beyond recognition and disappear. Empires would rise, dominate, and crumble into dust. Continents would shift. Mountain ranges would erode. New species would emerge. Others would go extinct. The golden record bolted to its side. Our message to potential finders containing greetings in 55 languages, Beethoven and Chuck Berry whale songs, whined thunder. A mother's heartbeat would arrive long after every language on that record had mutated into something unrecognizable, long after the civilizations that created that music had been forgotten. The engineers who built Voyager, who calculated its trajectory through the outer planets, who hand-tightened its bolts, who stayed up nights checking and rechecking the math, who wept when the first images of Jupiter arrived. Most of them are dead now. And Voyager is still at the beginning, still in the doorway, still by cosmic measures at home. There's a devastating poetry in this. Voyager 1 has escaped the sun's grasp. It has left the heliosphere. It drifts in true interstellar space, and yet it has barely moved. It will drift for millennia, carrying its golden message through emptiness, outliving Earth, outliving perhaps even the sun itself, and it will never arrive anywhere. Each photon from Alpha Centauri travels alone for 4.24 years. No companion, no confirmation it will be seen, just motion through absolute darkness, hoping that at the end of the journey, an eye will be waiting, and we, watching that light reach us, feel the same loneliness. Here on Earth, connection is instant. You call someone you love. Words travel as electromagnetic waves, light speed bouncing through satellites, arriving in fractions of a second. You speak, they hear. You laugh together in real time. But to Alpha Centauri, you send a message, "Are you okay?" It travels at light speed for 4.24 years. Arrives. They receive it. They respond, "I'm fine." Their response travels back. Another 424 years. Total time for one exchange, 8.48 years. Think about who you were 8 years ago. The things you cared about. The person you loved. The dreams you held. How much of that person still exists? By the time you hear, "I'm fine," you're not the same person who asked. They're not the same person who answered. The conversation isn't between two people. It's between two ghosts reaching across time, speaking to versions of each other that no longer exist. Imagine someone you love living on Proxima b. They send you a message, a goodbye. "I'm leaving. I can't do this anymore." You receive it 4 years later. 4 years after they spoke those words. 4 years after they made their decision. After they moved on, changed, became someone else entirely. After perhaps they stopped existing at all. And if you weep, if you scream into the transmission, if you pour out every word you should have said, they receive your tears 4 years after you cried them. 8 years, round trip. By then your grief is history, your love archaeology. Perhaps that's the true meaning of a light year. Not distance traveled, but time delayed. Not space crossed, but connection severed. The gap between speaking and being heard. Between reaching out and being touched. Light is the fastest thing in the universe, and it's not fast enough. We are creatures who evolved for instant feedback. Touch something hot, immediate pain. Call out, immediate echo. See a friend's face, immediate recognition. But the universe operates on different time scales. Light from distant stars is always a message from the past. Every observation is historical. Every image delayed. And between those delays in the silence, while light travels, we are alone. Completely, absolutely alone. So if light, the fastest thing to ever exist, isn't fast enough, if the very nature of the universe forces us to always be late, always behind, always looking into the past, then technology, the machines, we build, the engines we design, could they ever break through that wall? We made it to the moon. Why can't we make it to Alpha Centauri? July 20th, 1969, Neil Armstrong's boot touches lunar dust. One small step for man, one giant leap for mankind. The world watched and believed, this is only the beginning. If we reach the moon in 1 decade, then Mars in 2, then the stars in our lifetimes. The future felt inevitable. Progress felt unstoppable. The moon sits 384,000 kilometers away. A 3-day journey, close enough that radio signals arrive in 1.3 seconds. Close enough that if something goes wrong, you can still turn around and come home. Alpha Centauri sits 128,000 kilometers away. That's 104 billion times farther than the moon. If the moon landing was stepping out, your front door, reaching Alpha Centauri, is walking around the Earth 1 billion times. If Apollo 11 was a short drive to the grocery store. Alpha Centauri is circling the planet until the continents drift into new configurations. The Apollo program humanity's crowning achievement, the moment we became a spacefaring species, carried us 0.0% of the way to the nearest star, and we celebrated like we'd arrived. Chemical rockets, fire and fury, the technology that powered Apollo 11, that still powers every rocket we launch today. The principle is ancient elemental burn fuel, expel it backward, push forward, action and reaction. Newton's third law made thunder. It's beautiful, primal, magnificent, and completely utterly inadequate. The rocket equation, Tsiolkovsky's equation, governs all of this. It's simple mathematics with devastating implications. Imagine you're sitting on a sled on perfectly smooth ice. Frictionless. To move forward, you throw your backpack behind you. The momentum pushes you forward. Simple. But now you want to go faster. You throw your water bottle. Faster still, your jacket, then your shoes. Each item you throw gives you a little more speed. But here's the problem. The more you throw, the lighter you become. And the lighter you are, the less mass you have to throw. You're trapped in a loop. To go faster, you need fuel. But fuel is heavy. So you need more fuel to carry the fuel, which makes you heavier, which means you need even more fuel. The loop spirals into impossibility. To reach even 1% of a light speed, using chemical rockets 3,000 kilometers per second, you would need more fuel than exists in the observable universe. Not metaphorically, literally, more mass than all the stars, all the planets, all the matter we can detect across 93 billion light years. For every kilogram of spacecraft, you'd need 10 more 48 kilograms of fuel. That's a 1 followed by 48 zeros. More mass than in the entire Milky Way galaxy. Chemical rockets are magnificent for local journeys. Earth to orbit, orbit to moon, even Mars barely. But for interstellar travel, they're not just insufficient, they're laughable, absurd. A paper airplane attempting to cross an ocean. The Apollo program burned 3,000 tons of fuel to deliver 45 tons to the moon, a ratio of 67 to 1. 67 kilograms burned for every kilogram delivered. For Alpha Centauri, that ratio explodes beyond comprehension. The spacecraft becomes a grain of sand attached to a mountain of fuel, and that mountain grows faster than physics allows you to lift it. So, engineers dreamed of alternatives. Nuclear pulse propulsion. Project Orion conceived in the 1950s. The concept: detonate nuclear bombs behind your spacecraft. The explosion strikes a massive metal plate. The ship rides the shockwave like a surfer on an atomic tsunami. The calculations were done, peer-reviewed, published. It could work. Theoretically, you could reach 10% of light speed, arrive at Alpha Centauri in 43 years, within a human lifetime. The cost: 1 million nuclear warheads, detonated in sequence. One explosion every 3 seconds for a month straight. A continuous chain of atomic detonations, propelling a ship forward through the violence of splitting atoms. The engineering is sound. The physics checks out. The logistics are insane. Building 1 million nuclear bombs, launching them into space without one detonating prematurely, surviving the radiation exposure, the heat, the shock waves that would rattle the ship apart if the timing was off by milliseconds, the political impossibility of any nation or coalition agreeing to such a project. Project Orion died not because the physics failed, but because no sane civilization would attempt it. Ion drives, elegant, efficient, using electromagnetic fields to accelerate ions, charged particles, and expel them at extraordinary velocities, 10 times more efficient than chemical rockets. Theoretically perfect. The thrust generated equivalent to the weight of a single sheet of paper pressing against your palm. Ion drives work beautifully for slow, patient missions. The Dawn spacecraft used ion propulsion to visit Vesta and Ceres asteroids in our own solar system. It worked perfectly, and it took years to reach them. To accelerate a crewed spacecraft to interstellar velocities using ion propulsion, you'd need centuries of continuous thrust. The crew would be long dead before reaching meaningful speed. Their children dead. Their children's children dead. By the time you reached velocity, everyone aboard would be dust. Solar sails. Perhaps the most poetic solution. Vast mirrors kilometers across, catching photons from the sun. Each photon imparts a tiny push, infinitesimal momentum. But in the vacuum of space, with no friction to slow you, those tiny pushes accumulate. Over time, you accelerate, endlessly, using nothing but starlight. The appeal is undeniable. No fuel required, infinite range, pure physics. Elegant as the equation, beautiful as a poem. The problems are equally undeniable. A solar sail, large enough to accelerate meaningful payload, would need to span hundreds of kilometers, thinner than a human hair, lighter than a spider's web, perfectly reflective. Any imperfection, any wrinkle, any shadow, and the acceleration becomes asymmetric. The craft begins to tumble, and at the speeds required for interstellar travel, even the interstellar medium becomes lethal. Hydrogen atoms, just single protons, drifting in space, strike the sail with the kinetic energy of bullets. The sail wouldn't survive. It would shred like tissue paper in a hurricane, torn apart by atoms. Even if it survived the journey, there's no way to stop. You arrive at Alpha Centauri, traveling at 20% of light speed with no brakes. You flash through the system in hours, cameras clicking frantically, capturing blurred images before vanishing into the void forever. A cosmic drive-by shooting. Every solution collapses under scrutiny. Chemical rockets exponentially insufficient. Nuclear pulse propulsion politically impossible. Ion drives glacially slow. Solar sails fatally fragile. There's a moment every aerospace engineer experiences, alone, late at night, in a university lab or a corporate office or a home study, calculator in hand or equations on screen, working through the numbers one more time, hoping desperately, hoping for a different answer. Delta V requirements, Tsiolkovsky's equation, energy to mass ratios, radiation shielding thickness, life support duration, fuel consumption rates, and every single time the answer is the same. It doesn't work. None of it works. The numbers don't add up. The physics won't bend. The universe says no. Some of these engineers are old now, gray-haired, retirement approaching, or already arrived. They spent entire careers designing missions to Mars, to Jupiter's moons, to Saturn's rings, always dreaming that the next generation would go farther, that somehow someone would solve it. Werner von Braun, architect of the Saturn V rocket, the machine that sent Apollo to the moon, stood in 1969 and declared Mars within 10 years. He died in 1977. We still haven't sent humans to Mars. Mars is 225 million kilometers away on average. Alpha Centauri is 40 trillion kilometers away, nearly 200,000 times farther. There's a cruelty embedded in this reality. We can imagine Alpha Centauri with perfect clarity. We can see it through telescopes, photograph its light, measure its spectrum, calculate the mass of Proxima b, estimate the temperature of its twilight zone. We can envision standing on that alien world, feeling red light on our skin, looking up at the binary stars glowing like pearls in a crimson sky. Our imagination has no limits. But our bodies do. Our machines do. Physics does. We can dream of places our technology will never reach. We are prisoners who can see through the bars with perfect clarity, but cannot open the door. We stand at the window of the universe, faces pressed to the glass, watching wonders we can describe, but never touch. Perhaps the problem isn't the machines. Perhaps the machines are performing exactly as physics allows. Perhaps they're not failing us. Perhaps they're revealing the truth we don't want to accept. Perhaps the failure isn't technological at all. Perhaps the failure is us. If machines cannot carry us, perhaps our bodies can endure what technology cannot. If we cannot fly fast enough, perhaps we can live long enough. Perhaps the problem isn't speed, but fragility. You were born to live on Earth, and only on Earth. Every atom in your body was forged in the heart of a dying star billions of years ago. But the life those atoms assembled into is exquisitely, devastatingly fragile, built for one specific gravity, one specific atmospheric pressure, one specific magnetic field strength. Step beyond those invisible boundaries, and your body begins to come apart. Microgravity, weightlessness, the word sounds peaceful. Astronauts float through the International Space Station like dancers, graceful and serene. It looks like freedom. Inside their bodies, catastrophe unfolds in silence. Within days of entering orbit, your bones begin to dissolve. Calcium leaches from your skeleton into your bloodstream at a rate of 1 to 2% per month. On a 6-month ISS mission, astronauts lose up to 20% of their bone density in weight-bearing bones, hips, spine, femurs, tibias. On Earth, every step you take compresses your skeleton. Your bones feel that stress and respond by reinforcing themselves, constantly building, constantly strengthening. It's an endless conversation between gravity and biology. In space, that conversation ends. Your bones feel no load, no stress. Your body, efficient, as always, decides why waste resources maintaining something we don't need, and begins dismantling your skeleton, quietly, efficiently, without pain, until you try to return to gravity. Imagine traveling to Alpha Centauri, even at an impossible 10% of light speed, requiring 43 years, and arriving with bones so porous, so brittle, that stepping onto a planet's surface fractures your femur, that a mild stumble shatters your spine, that your skeleton, the literal framework, holding you upright, has become dust inside you. You would arrive at another star unable to walk on its world. Muscles deteriorate even faster. In microgravity, your body doesn't need strength. Your heart doesn't need to pump blood upward against gravity's pull. Your calves don't need to support your weight. Your core doesn't need to hold you upright. Within weeks, muscle mass begins to vanish. Astronauts lose 20% of muscle volume in 5 months. Their legs shrink, their arms weaken, even their heart's muscular organs pumps, evolved to work against Earth's gravity, grow smaller, lazier, weaker. When you return to gravity, your cardiovascular system can't cope. Standing up causes dizziness, fainting. Blood pools in your legs. Your weakened heart struggles to circulate it back up to your brain. Some returning astronauts can't stand for more than a few minutes without collapsing. For a multi-decade journey to Alpha Centauri, this isn't manageable deterioration. This is disqualification. You can't send humans on a 40-year voyage if they'll arrive too weak to survive on a planet with gravity. Then there's the fluid shift. On Earth, gravity pulls blood and fluids downward into your legs. Your body compensates automatically, maintaining equilibrium. In space, fluids redistribute upward. Blood surges into your head and upper body. Your face swells. Your sinuses congest. You feel perpetually like you're hanging upside down. Astronauts call it puffy face syndrome, but the most insidious effect happens behind your eyes. Cerebrospinal fluid, the liquid cushioning your brain and spinal cord, increases pressure inside your skull. That pressure presses against the back of your eyeballs from the inside. Over months, this constant pressure flattens your eyeball, distorting its shape. Astronauts return from 6-month ISS missions with permanent vision changes. Some develop hyperopia farsightedness. Others experience structural deformation of the optic nerve. The medical term is ZIP, visual impairment and intracranial pressure syndrome. There's no treatment. The damage accumulates. It's irreversible. Imagine traveling 43 years to Proxima b and arriving functionally blind, able to see shapes perhaps, colors, but not details, not faces, not the alien world you crossed 4 decades of void to witness. But even if your bones survived, even if your muscles held, even if your vision remained intact, radiation would kill you. Earth's magnetic field surrounds our planet like an invisible fortress. Solar wind streams of charged particles from the sun strikes this field and deflects harmlessly away. Cosmic rays, high-energy particles accelerated by distant supernovae curve around it, bent away by forces we never see, never feel. We live inside a protective bubble, an electromagnetic womb. Step outside it, and the universe's radiation bombardment begins immediately. On the ISS, still within Earth's magnetosphere, only 400 kilometers up, astronauts receive approximately 150 millisieverts of radiation per year. That's equivalent to about 8 chest X-rays per day, every single day. In deep interstellar space, beyond any magnetosphere, radiation exposure increases 100-fold or more. Galactic cosmic rays, high-energy protons, helium nuclei, heavy ions, traveling at relativistic speeds, significant fractions of light speed themselves. They strike your body and pass straight through skin, through muscle, through bone, through the nucleus of your cells. Where they pass, they shred DNA, not clean breaks that your cells can repair, complex tangled breaks, multiple strands severed simultaneously, unrepairable damage. Your cells try, they have repair mechanisms, but cosmic rays cause catastrophic damage. The cell either dies or mutates. Multiply this across trillions of cells, across months, years, decades. Cancer becomes not a risk, but a certainty. Not might happen, will happen. Studies estimate a 2-year Mars mission, a fraction of Alpha Centauri's distance, still within the sun's protective influence, carries a 30% increased lifetime cancer risk. For interstellar travel, lasting decades, the numbers become meaningless. Cancer is guaranteed. You could build shielding, meters-thick walls of lead or water surrounding the spacecraft. But remember, the rocket equation, every kilogram of shielding requires exponentially more fuel. The mass becomes prohibitive. The design collapses back into impossibility. Some propose electromagnetic shielding, generating artificial magnetic fields around the ship strong enough to deflect charged particles. The power requirements are staggering. Maintaining a field strong enough for decades would consume energy equivalent to a small city continuously for 40 plus years. Even your brain isn't safe. Cosmic rays passing through neural tissue cause cosmic ray visual phenomena. Flashes of light astronauts see with their eyes closed. Each flash represents a particle tearing through their optic nerve or visual cortex, leaving microscopic trails of damage. Prolonged exposure causes cognitive degradation, memory impairment, slower reaction times, personality changes. Not immediately obvious, but cumulative, progressive, irreversible. By the time you reached Alpha Centauri, after 4 decades of cosmic ray exposure, you might not remember why you left, who you were, what you were trying to reach. But perhaps the cruelest betrayal isn't physical, it's psychological. Astronauts on the ISS orbit Earth every 90 minutes, 16 sunrises per day. They look down and see home cities glowing at night, weather systems swirling coastlines they recognize. They're isolated but not alone. Radio contact is instantaneous. Family can speak to them in real time. If something catastrophic happens, rescue missions can launch within days. Now imagine Alpha Centauri. No Earth visible in any window. No sunrise, just unchanging starlight. No horizon. No sky. No sense of day or night, except what the ship's computer arbitrarily decides. The same metal walls. The same recycled air. The same 5 or 6 faces, if you're not traveling alone, for 40 years. Psychology studies show that isolation for even 6 months causes measurable psychological changes: depression, anxiety, difficulty concentrating. Some astronauts report feeling detached from reality after extended missions. The Mars 500 experiment, a simulated Mars mission where 6 people spent 520 days in isolation, showed that after 200 days, crew members stopped communicating with each other voluntarily. They retreated into private spaces, avoided eye contact. The social fabric began to fray. That was less than 2 years in a simulation on Earth, with the knowledge they could leave if absolutely necessary. For Alpha Centauri, 43 years minimum. No possibility of turning back. No rescue, no escape, just forward motion through endless dark. The human mind wasn't built for that. We evolved for seasons, for weather, for sunrise and sunset, for forests and oceans, and the simple comfort of knowing Earth continues beneath our feet. Remove all that. Remove every environmental cue that tells you you're alive, that you're human, that you belong somewhere, and the mind begins to dissolve. Not dramatically, quietly, like bones in microgravity, a slow coming apart. Generation ships the theoretical solution where 10 or 20 generations live and die aboard a vessel passing the mission. Like an inheritance, face an even darker problem. The 5th generation will ask, why are we doing this? They never chose the mission, never saw Earth, don't remember what they're traveling toward, or why their ancestors thought it mattered. All they know is metal corridors and recycled air, and the burden of a promise made by dead people they never met. Psychological studies of isolated communities show that without external purpose, social structures collapse. Biosphere 2, 8 people sealed in an enclosed environment for 2 years, ended in internal conflict. Factions formed. Trust disintegrated. How do you maintain faith in a mission longer than any civilization has survived. How do you pass meaning across 20 generations when each generation's lived experience is imprisonment on a ship going nowhere? They can see cryosleep, the science fiction dream of freezing people for the journey, faces its own insurmountable problems. Freezing destroys cells. Ice crystals form. They expand. They rupture cell membranes from the inside, shred tissue like microscopic knives. Cryoprotectants chemicals that prevent ice formation are toxic in the concentrations required for whole body preservation. And even if you could preserve the body without damage, there's consciousness. Memory is not data stored on a hard drive. It's a living pattern of electrical and chemical connections, constantly shifting, constantly active. What happens when you stop that pattern for 40 years? When you restart it, is it the same pattern? Are you the same person tardigrades can survive freezing, desiccation, radiation, but they don't have consciousness? They don't have memory or identity or the sense of continuous self that makes you you. You might be able to freeze a body and revive it, but you, the pattern of awareness, reading these words right now, would that survive? Or would it be someone else waking up, someone who inherited your face and memories? But isn't you a philosophical zombie, wearing your identity like a suit? There's a revelation buried in all this fragility. Every atom in your body came from stars. But to return to the stars, your body would need to become something it's not, something it cannot be. You were designed by evolution, by billions of years of adaptation for 1 g of gravity, for 1 atmosphere of pressure, for 24-hour days, for Earth. Outside those parameters, you are a fish pulled from water, gasping, slowly dying. Perhaps we were never meant to leave. Perhaps we evolved to look at the stars, to wonder about them, to dream of touching them, but not to actually go. Perhaps our role in the universe is to witness, not to wander. We've seen the destination. We've built the machines. We've dreamed the dream. Now comes the reckoning, the moment when mathematics looks you in the eye and says no. There are equations that kill dreams. This is one of them. Somewhere in a university library, perhaps late at night, perhaps in the quiet hours before dawn, a student sits alone, calculator glowing in the darkness, pencil scratching against paper. They're working through the numbers for the 100th time, checking and rechecking, hoping desperately for a different answer. The question is simple. How much fuel do we need to reach Alpha Centauri? The answer breaks everything. The Tsiolkovsky rocket equation, written in 1903 by a Russian school teacher who never built a rocket but understood the mathematics of motion. It's elegant, concise, devastating. Let me translate it without symbols, without Greek letters, without the language that hides its cruelty. Imagine you're in a canoe on perfectly still water. No current, no wind. To move forward, you throw rocks backward. Each rock you throw pushes you forward a little. Simple physics, action and reaction. But here's where it gets complicated. To throw rocks, you need to carry rocks, and rocks are heavy. So the more rocks you carry, the heavier your canoe becomes, which means each rock you throw moves you forward less than the previous one because you're heavier. So you think, I'll just bring more rocks, but more rocks make you heavier, which means you move forward even less per rock, which means you need even more rocks, which makes you heavier still. This is the loop, the spiral, the mathematical trap. that has no escape. For interstellar travel, the numbers become obscene. To accelerate a spacecraft to 90% of light speed fast enough to reach Alpha Centauri in about 5 years, using conventional rockets, you would need fuel equal to 10 to the power of 48 times the mass of your spacecraft. That's a 1 followed by 48 zeros. To put that in perspective, there are approximately 10 to the power of 53 atoms in Earth. You would need fuel mass equivalent to 100,000 Earths for every kilogram of spacecraft. The entire observable universe contains about 10 to the power of 53 kilograms of matter. You would need more fuel than exists in all the galaxies, all the stars, all the planets we can detect across 93 billion light years of space. The equation doesn't say it's difficult. It says it's impossible. Not, we haven't figured it out yet, impossible. Fundamentally, mathematically, absolute impossible. A student somewhere closes their notebook, turns off the calculator, sits in the dark, and realizes every physicist who came before them saw the same numbers, and every physicist who comes after will see them too. The dream doesn't die from lack of trying, it dies from arithmetic. But perhaps mass isn't the only problem. Perhaps we're thinking about this wrong. Perhaps instead of carrying fuel, we could just go faster. After all, Einstein's equations allow objects with mass to approach if never reach the speed of light. So let's explore that. Let's see what happens when you try to accelerate to relativistic speeds. When you start chasing light itself, Einstein's famous equation, energy equals mass, times the speed of light squared, isn't just about atomic bombs and nuclear power. It's about the structure of space-time itself, and it contains a devastating truth about motion. As an object accelerates, it gains mass. Not metaphorically, not it feels heavier. It actually physically, measurably becomes more massive. At everyday speeds, car, airplane, even spacecraft, this effect is negligible, unmeasurable. Your car doesn't gain weight when you accelerate down the highway, but approach the speed of light, and the effect becomes catastrophic. At 10% light speed, 30,000 kilometers per second, your mass increases by about 0.5%, barely noticeable. A 1,000 kilogram spacecraft now weighs 1.5 kilograms, manageable. At 50% light speed, your mass increases by 15%. That same spacecraft now weighs 155 kilograms, noticeable, but perhaps workable. At 90% light speed, you're 230% heavier than when you started. Your 1,000 kilogram craft now masses 200-300 kilograms, more than double. At 99.9% light speed, your mass has increased by 22.366%. You are now 224 times heavier than at rest. That 1-ton spacecraft weighs 224 tons. And here's the trap. The heavier you are, the more energy required to accelerate further, which means you need more fuel. But fuel has mass, which makes you heavier, which requires more energy, which requires more fuel. The same spiral, the same impossible loop. As you approach light speed, your mass approaches infinity. An accelerating infinite mass requires infinite energy. The universe doesn't forbid you from reaching light speed. It just makes you infinitely heavy first. So heavy that all the energy in the universe couldn't push you faster. This isn't an engineering problem. This is the architecture of reality. Space-time itself conspires to keep matter slow, to ensure that light and only light travels at the cosmic speed limit. We are forever trapped below it, forever slow, forever late. But even if we could somehow solve the mass problem, even if we found some exotic propulsion that didn't require carrying fuel, even if we built a ship that could accelerate to 20% of light speed, a velocity far beyond anything we've achieved, there's another problem. The emptiness between stars isn't empty. Space contains, on average, about one hydrogen atom per cubic centimeter. That sounds like nothing. Perfect vacuum. Negligible. At 20% of light speed, 60,000 kilometers per second, those atoms become bullets. Kinetic energy equals 1/2 mass times velocity squared. At relativistic speeds, even a single proton carries tremendous energy. A hydrogen atom striking your spacecraft at 60,000 kilometers per second hits with the energy of a hand grenade. Not metaphorically, actually. The kinetic energy of that single proton is equivalent to a military explosive. Scale that up. Your ship is traveling through interstellar space for 20 years. You're encountering trillions upon trillions of atoms, each one a micro explosion against your hull. At 50% light speed, those atoms strike with the force of artillery shells. At 90% light speed, each atom becomes a bomb. The empty space between stars transforms into a shooting gallery, a cosmic minefield where every speck of hydrogen becomes lethal. You would need shielding meters thick, which adds mass, which requires more energy, which brings us back to the rocket equation, which collapses back into impossibility. Every solution spawns 3 new problems. Every answer reveals deeper questions. Every path forward circles back to the same mathematical walls. And then there's the problem we forgot about entirely. The one that doesn't appear in the equations until you've already solved everything else. How do you stop imagine? Through some miracle of engineering, you've built a spacecraft. You've solved the fuel problem. You've accelerated to 20% light speed. You've shielded against interstellar hydrogen. You've survived the journey. After 21 years, you arrive at Alpha Centauri. You're traveling at 60,000 kilometers per second, and you have no brakes. To slow down, you need to expend the same energy you used to speed up. Every joule spent accelerating must be spent again, decelerating. If it took the mass energy equivalent of a small star to reach 20% light speed, it takes the same amount to stop. Most proposed missions, Breakthrough Starshot, for example, don't even attempt to stop. Their flybys flash through the Alpha Centauri system. In hours, cameras snapping frantically, gathering what data they can before vanishing into the endless dark beyond. 21 years to arrive, 4 hours in the system, then infinity in the void. You could try using the destination star's light to slow down, unfurling your solar sail backward, catching photons to break. But the deceleration would take decades. By the time you slowed enough to orbit, you'd have drifted far past the system. Or you could carry fuel for deceleration. But remember the rocket equation. If you need X fuel to accelerate and X fuel to decelerate, you now need fuel to carry that deceleration fuel. The mass multiplies exponentially. The numbers explode beyond reason. Every solution becomes its own impossibility. There's a laboratory somewhere, empty now. Late afternoon light slanting through dusty windows. On a whiteboard, equations stretch across the entire wall. Delta V calculations, energy requirements, mass ratios, decades of work. At the bottom in small letters, someone has written, "It doesn't work." The professor who wrote that, who spent 40 years designing theoretical missions to nearby stars, retired last year. In their farewell lecture, they said something that haunted every student in the room. I spent my life calculating how to reach the stars. The mathematics says don't, not don't yet, not with current technology, just don't. The universe isn't cruel, it's honest. It shows you the numbers without deception, and the numbers say that some dreams, no matter how beautiful, no matter how badly we want them, are not meant for reaching. Perhaps that's the hardest truth. There are dreams so beautiful that it's better not to know they're impossible. Dreams that give meaning to the struggle, purpose to the reaching, even when arrival is forever out of grasp. The mathematics breaks hearts, not because it says no, but because it explains exactly why, with precision, with certainty, with equations that anyone can verify and no one can refute. Some questions have answers. This one has a proof, and proofs don't negotiate. So, if humans cannot go, perhaps we send something smaller, lighter, something that doesn't need life support or food or hope. Perhaps we send machines to dream on our behalf. If the body cannot travel, let the machines go in our place. There's a certain grief in this admission, an acceptance that we will never feel alien soil beneath our feet, never breathe air under a crimson sky, never look up and see Earth as a distant point of light. But grief at least is honest, and from honesty comes a different kind of hope. If we cannot send ourselves, perhaps we can send our eyes, our instruments, our curiosity distilled into silicon and steel. Breakthrough Starshot, announced in 2016, funded by Yuri Milner, supported by Stephen Hawking, designed by some of the brightest minds in physics and engineering. The most serious attempt yet to reach another star system within a human lifetime. The concept is audacious. Instead of massive spacecraft requiring impossible fuel, send something tiny. Spacecraft the size of a postage stamp, weighing only a few grams, attached to sails just a few meters across reflective surfaces, thinner than a strand of human hair. From Earth fire, an array of ground-based lasers, a combined power of 100 gigawatts, roughly the output of 100 nuclear power plants focused into a tight beam. Aim that beam at the tiny sails. For 10 minutes, the lasers fire. The light pressure photons striking the sail accelerates the craft. Faster and faster. In those 10 minutes, the probe reaches 20% of the speed of light, 60,000 kilometers per second. 20 years to Alpha Centauri. 24 years total for the first images to return to Earth. The elegance is undeniable. No fuel, no rocket equation, just light pushing against a mirror, accelerating a grain-sized probe to relativistic speeds. The cost, $10 billion. For comparison, the Mars Perseverance rover cost $2.7 billion. The James Webb Space Telescope, $10 billion. The entire Apollo program, adjusted for inflation, $280 billion. $10 billion to reach another star seems almost reasonable until you examine the problems. Problem 1, aiming. You're trying to hit a sail 4 meters across from Earth's surface. The sail will be accelerating, moving faster every second. The target is not just a small, but mobile shifting position. As photons push it forward, the laser must track perfectly for 10 minutes. Any deviation, atmospheric turbulence, thermal expansion of the laser array, minor earthquakes, cloud cover, and the beam misses. The probe tumbles. The mission fails. It's like firing a rifle in New York City and hitting a grain of sand in Tokyo, while the sand is accelerating, while wind blows, while the earth rotates beneath you. Possible, perhaps. Reliable. Not with current technology. Problem 2, survival. At 20% light speed, a single atom of interstellar hydrogen strikes with the energy of a grenade. Remember the math from earlier? A gram mass probe encountering a dust grain, something a millimeter across, nearly weightless, experiences an impact equivalent to a cruise missile. The interstellar medium isn't perfectly empty. It contains gas, dust, microscopic particles. Your probe must travel through 40 trillion kilometers of this material. The odds of hitting something nearly certain. One collision, and the probe is vaporized instantly, completely. After $10 billion and 20 years of waiting, after humanity held its breath in anticipation, nothing, just silence, just darkness. You could send hundreds of probes, accepting that most will fail. But each failure is $10 billion. How many can we afford to lose before the project becomes politically untenable, before funding dries up, before people ask, why are we throwing money at specks that die in the dark? Problem 3, communication. Your probe masses a few grams. It has no room for a large transmitter, no power source beyond tiny solar panels. At Alpha Centauri, it must send data back across 4.24 light years, using a transmitter smaller than your fingernail. The signal will be weaker than a whisper in a hurricane, fainter than the cosmic background radiation. To detect it, we'll need radio telescopes operating at the absolute edge of sensitivity, listening to a specific frequency, hoping to detect a pattern buried in noise. And the probe will be traveling at 60,000 kilometers per second. It won't orbit. It won't slow down. It will flash through the Alpha Centauri system in hours, perhaps 4 or 5 hours total. Whatever data it gathers, it must transmit immediately. There are no second chances. Imagine spending 24 years waiting. A generation of scientists growing old, checking the instruments every day, hoping for signal. And then 4 hours. 4 hours to capture everything humanity has dreamed of knowing about our nearest neighbor. Point the instruments wrong, miss it. Data corruption. During transmission, lose it. Equipment failure after 20 years in the void. Gone. All or nothing. Everything dependent on a device smaller than a credit card. Traveling faster than anything humans have built. Surviving conditions that would obliterate steel. Transmitting data we might not even detect. What would we actually see? If Breakthrough Starshot succeeds, and that's an enormous if the images returning in 2069, assuming a 2045 launch, would be pixels, blurry low-resolution pixels, perhaps enough to confirm Proxima b exists, perhaps spectroscopy data showing atmospheric composition, maybe if we're extraordinarily lucky enough, information to determine if the planet has water, oxygen potential biosignatures, but no photographs of alien cities, no high-definition panoramas of red skies and binary stars, no close-ups of alien oceans, just data, raw, compressed, barely detectable data that scientists will spend years analyzing, and humanity will wait. An entire generation will live and die between launch and data return. The people who designed the mission will be elderly or dead when the first images arrive. The political landscape will have shifted, funding priorities changed, technologies advanced beyond what we imagined. 24 years is longer than most careers, longer than most marriages, longer than childhood, adolescence, and young adulthood combined. You could be a teenager when Breakthrough Starshot launches, middle-aged when the data returns. Your children might see the results. Your children's children will read about it in history books. And yet, there's something beautiful in this patience, in accepting that some discoveries outlive their discoverers, that humanity can begin projects our grandchildren finish. Voyager carries that same bittersweet poetry, the golden record, attached to both Voyager 1 and Voyager 2, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life on Earth. Greetings in 55 languages, music from Bach, Beethoven, Chuck Berry, Javanese gamelan, Peruvian panpipes, natural sounds, wine thunderbirds wails, a human heartbeat, laughter. Instructions for playing it are etched on the cover, a pulsar map showing Earth's location, diagrams explaining human biology, mathematics, and physics in universal language. It's a message in a bottle thrown into an ocean that has no shore. Voyager will never reach Alpha Centauri. It's not headed that direction. In 40,000 years, Voyager 1 will pass within 1.6 light years of the star Gliese 445. By then, every human who built it will have been dead for 38,000 years. Civilizations will have risen and fallen. Languages evolve beyond recognition. Perhaps humanity itself will be gone. But the golden record will still be playing its message, still carrying whale songs through the void, still offering to anyone who might find it proof that once briefly, impossibly, a species on a small blue world looked up and tried to say hello. The question haunts, if someone finds it 1 billion years from now, will Earth still exist? Will there be anyone left who remembers the hands that built it, the voices recorded on it, the hope encoded in its grooves? Voyager will outlive everything. It will drift through the galaxy long after the sun has swelled into a red giant and consumed the inner planets, long after Earth is ash. It will carry our laughter into a future where no one remains to laugh. There's something heartbreaking in that image, and something transcendent. Perhaps this is what reaching the stars actually means. Not bodies on distant worlds, but messages, echoes, proof that we existed, that we wondered, that we tried. We send machines because we cannot go ourselves. We send recordings because our voices cannot carry through vacuum. We send mathematics because it's the only language we trust will be understood. And in doing so, we admit something profound. The act of reaching out matters more than arrival. The message matters more than the messenger. Breakthrough. Starshot, if it launches, will not carry humans. It will not even carry human artifacts. No golden record, no plaques, no photographs. Just instruments, silicon and sensors. Technology stripped down to pure function. But every byte of data, it returns every pixel, every spectral line, every measurement will be a love letter humanity wrote to the universe, saying, we saw you, we wondered about you, we reached toward you, even knowing we might never touch. These probes are not failures because they're not human. They're something else entirely. They're the part of us that can travel, the part that doesn't need breath or warmth or hope to continue. They're our curiosity made metal, our wonder made light, our longing transformed into something that might survive the journey we cannot make. And perhaps that's enough. But machines, for all their resilience, cannot dream. They cannot wonder. They cannot experience. So what if we sent something else Not our bodies, not our machines, but our minds themselves. If the body is a prison, can consciousness escape? The human brain contains approximately 86 billion neurons. Each neuron connects to thousands of others through synapses, connection points, where electrical signals jump from one cell to the next. In total, roughly 100 trillion connections, 100,000 billion pathways along which thought travels. Every memory you have, every emotion you feel, every decision you make, every sensation of being you, all of it emerges from the pattern of signals flowing through this network. So, here's the question that keeps neuroscientists awake at night. If we could scan that pattern completely, map every neuron, every synapse, every electrical pulse, and recreate it inside a computer, would that be you? The theory is seductive. Upload your consciousness to a digital substrate. Your mind becomes data, pure information, and information travels at the speed of light. Send that data to Alpha Centauri, 4.24 years. A machine receives the transmission, reconstructs the pattern. Your neurons, your synapses, your memories all rebuilt in silicon instead of cells. And you wake up, not your body, you, your consciousness, your sense of self, opening digital eyes on an alien world 40 trillion kilometers from where you closed them. Your body remains on Earth, dies perhaps, buried or burned. But you, the pattern, the information, the essence continues. Immortal, unbound by flesh, free to travel the universe as data packets racing through the void. It's beautiful, elegant, the perfect solution to every biological limitation we've discussed. Except for one small problem. Is it you, the ship of Theseus? An ancient thought experiment. A ship sails for decades. Over time, every plank is replaced, every sail, every nail. Eventually, not a single original piece remains. The question, is it still the same ship? Now apply that to consciousness. If we scan your brain and upload the pattern to a computer, we're not moving you. We're copying you, creating a duplicate, a pattern that matches yours exactly. That copy will have your memories, your personality, your hopes, fears, preferences, quirks. It will believe absolutely, completely that it is you, because it has all your memories of being you. It will remember this moment, remember reading these words, remember deciding to upload. But if the original you is still standing there after the upload, completes, still breathing, still thinking, still feeling, then who is the copy? Imagine the moment of upload. You lie down. Scanners map your brain at molecular resolution. The process completes. A voice announces, upload successful. The signal is being transmitted to Alpha Centauri, and you sit up, still in your body, still on Earth. You look at the computer screen showing transmission progress. 24 years remaining. In 424 years, something will wake up at Alpha Centauri with your memories believing it's you, but you're still here, still alive, still experiencing continuity of consciousness. So who is real? The original, the copy, both neither. If you're still here, then what traveled wasn't you. It was a copy, a very convincing copy, but a copy nonetheless. And if to make the upload work, the original must die. If scanning destroys the brain in the process, then you didn't escape death. You just created a successor, someone who will live your life after you're gone, who will think they're you, who will have all your memories of hoping to reach the stars. But you, the you, reading this right now, the continuous stream of experience that has been your entire life that ends, dies, stops. Every night you sleep, consciousness fades. For hours, you cease to experience anything. Then, morning comes. You wake. Consciousness resumes. Are you the same person who fell asleep? Or are you a new person with memories of being yesterday's person? Philosophy has wrestled with this for millennia. The continuity of self. Most of us have to assume that we remain the same person across sleep, across time, across change, because the alternative is too disturbing. But what if continuity requires more than just memories? What if it requires unbroken experience, an uninterrupted stream of consciousness linking one moment to the next? Sleep might be acceptable because it's temporary, shallow. Brain activity continues. The pattern never fully stops, just quiets. But upload, that's different. The pattern stops completely, then restarts elsewhere. A gap, a break, a death. Perhaps you is not a thing, but a process, a continuous process. Like a flame, you can light a new candle from an old one. The new flame looks identical, burns the same way, but it's not the same flame. The original flame went out. What continues is a copy. If consciousness is a process that requires continuity, then stopping it, even for an instant, ends it. What restarts is something new, something that believes it's you, but isn't. This isn't just philosophy, it's practicality. We haven't successfully scanned a complete worm brain yet. The nematode C. elegans has 302 neurons. We've mapped them. We know which neurons connect to which. But recreating the pattern in software, making a digital worm that behaves like a real worm, we haven't managed it. Humans have 86 billion neurons, nearly 300 million times more complex than the worm we can't simulate. If we could scan a human brain at the resolution required to capture everything, every neuron, every synapse, every chemical concentration, every electrical state, the file size would be approximately 2.5 petabytes. That's $2,500,000 gigabytes, 2.5 million gigabytes. To put that in perspective, a high-quality movie is about 5 gigabytes. Your consciousness would be equivalent to 500,000 movies. Sending that file to Alpha Centauri via radio transmission, even at light speed, takes 4.24 years. Nothing can speed it up. Information is bound by the same light speed limit as matter, and that assumes we can scan it, assumes we can digitize consciousness, assumes the pattern once stopped and restarted produces the same experience. Every assumption is enormous. Every step requires technology we don't have and fundamental questions we can't answer. Reality check. We're at least 200 years away from this technology, if it's possible at all. But suppose it becomes possible. Suppose we solve every technical challenge. Suppose consciousness can be uploaded, transmitted, reconstructed. Who gets to go first? Not everyone. The technology would be extraordinarily expensive, restricted, available only to those with resources, the ultra-wealthy, the powerful, the elite. They upload, they transmit themselves to colonies on distant worlds. They live forever in digital substrates that don't age, don't decay, don't die, and they can copy themselves, create backups, restore from earlier versions. If something goes wrong, one person becomes 10, 10 become 1,000, 1,000 become 1,000,000. Each copy believes truly, genuinely believes it's the original. Each has the same memories, the same identity. Each thinks, I uploaded successfully, I'm still me. But somewhere in that multiplication, something breaks. If there are 1,000,000 copies of you, which one is real? All of them. None of them. The original, the biological, you died long ago, 1,000 years ago. But the copies don't know. They can't know. They have memories of uploading, of continuity. They experience themselves as continuous with the biological you. But they're not. They're echoes, patterns repeating, simulacra of consciousness perhaps, but not the original experience. There's a horror in this that's worse than death. Death, at least, is final, known, complete. But this, you might already be dead, might have died 1,000 years ago. And what's reading these words right now? What thinks it's you might be copy number 847-392, running in a simulation unaware that the real you ended long ago. You'd have no way to know, no way to tell. The simulation is perfect. Your memories are intact. Your sense of self is complete, but you're a ghost, a digital phantom, consciousness without origin, experience without experiencer. Perhaps that's the true cost of immortality. Not that we'd live forever, but that we'd never know if we're truly alive. We want to live forever. The desire is ancient, primal. Every culture, every religion has grappled with it. Immortality, eternal life, escape from death. But if living forever means losing yourself, if the price of immortality is becoming something that only believes it's you, then is that life? Or is it the most complete death possible? The death of identity itself. Here's the thought experiment that breaks everything a button. Press it, and your consciousness uploads to a machine at Alpha Centauri. The signal transmits. In 4.24 years, you wake up on an alien world. But pressing the button kills the biological you, instantly, painlessly, but permanently. The copy will have all your memories, will believe itself continuous with you, will experience no break. From its perspective, it pressed the button and immediately arrived at Alpha Centauri. But you, the you deciding whether to press, will die, will cease, will experience nothing beyond the moment of pressing. Do you press it? If yes, you accept that you is just information, that continuity is illusion, that consciousness can be copied, transferred, moved like data. If no, you believe consciousness requires something more, something that can't be copied, something that ends when the brain stops, regardless of whether a perfect copy exists elsewhere. There's no right answer, just the question, hanging in the air like a blade. Perhaps the only way to reach the stars is to accept that we, as we are, as continuous experiencing beings, cannot go. Only our information can go, our patterns, our echoes, and maybe that's enough. Maybe consciousness doesn't require continuity. Maybe we're already discontinuous, dying every night in sleep, reborn every morning, linked only by memory. Or maybe we're fooling ourselves, constructing elaborate justifications for sacrificing the one thing we can never recover, the continuous experience of being alive. The stars call, but the price might be everything we are. Perhaps uploaded consciousness is too uncertain, too philosophical, but science fiction offered another escape, one that sounds more solid, more real, one written in the mathematics of general relativity, itself the warp drive. Science fiction gave us the warp drive. Real science gave us mathematics and tears. Every child who watched Star Trek absorbed the same beautiful lie. Faster than light travel is just engineering. Build the right engine, generate enough power, wrap space-time around your ship like a bubble, and the universe opens. Warp 1, Warp 5, Warp 9. The numbers increased like gears on a car, as if speed were just a matter of pressing the accelerator harder. It felt real, looked real, The science consultants used actual equations. The tech manuals described warp coils and plasma injectors and antimatter reactions with convincing specificity. And in 1994, physicist Miguel Alcubierre proved it wasn't entirely fiction. He published a paper showing that general relativity, Einstein's equations, describing how mass warps spacetime, technically allows a spacecraft to travel faster than light, not by moving through space, but by moving space itself. The concept is elegant. Imagine standing on a carpet. Instead of walking across it, you reach down and pull the carpet toward you. You haven't moved. The carpet has. But relative to the room, you've changed position. The Alcubierre drive works similarly. The spacecraft sits inside a bubble of normal spacetime. In front of the bubble space, contracts, distances shrink. Behind the bubble space, expands, distances grow. The ship doesn't move. Space moves around it. The bubble surfs through spacetime like a wave. Since the ship isn't technically moving through space, since space itself is moving, the light speed limit doesn't apply. You're not traveling faster than light. You're standing still while space carries you faster than light would travel through normal space-time. It's breathtaking, a legitimate solution to Einstein's equations. Peer-reviewed, published. Real mathematics suggesting faster than light travel might be possible until you read the requirements, the catch, the reason. Warp drives remain firmly in fiction comes down to two words: negative energy. To warp space-time, the way Alcubierre's equations require, you need matter with negative mass, not antimatter, negative mass, matter that weighs less than nothing, that pushes instead of pulls, that falls up instead of down. We've never found it, never detected it, never seen any evidence it exists anywhere in the universe. Quantum field theory hints that negative energy might exist at subatomic scales for infinitesimally brief moments, exotic quantum states, virtual particles, Casimir effect. But these are fleeting fluctuations, not stable matter you can harvest and use. To power an Alcubierre drive, you'd need negative mass equivalent to Jupiter's mass, the entire planet, but negative, continuously stable. And even if somehow you found or created that much negative mass, you'd need energy to shape it, to maintain the warp bubble, to contract space ahead and expand it behind. How much energy? Approximately 1 billion times the energy the sun outputs per second, continuously, for the duration of the flight. The sun produces about 400 trillion watts of power every second. You'd need 1 billion times that to power one ship. We barely harness 1 billionth of the sun's energy reaching Earth. The idea of generating energy 1 billion times greater than the sun's entire output is so far beyond our capabilities that it's meaningless. But perhaps the most fundamental problem isn't engineering, it's causality. If you can travel faster than light, relativity allows you to arrive before you left. Time travel, not metaphorically, actual time travel into the past. Special relativity links space and time. Events that are simultaneous in one reference frame occur at different times in another. At faster than light speeds, this effect becomes extreme. You could travel to Alpha Centauri, turn around, and return to Earth before you left. You could meet yourself. You could prevent your own departure. The grandfather paradox. You go back in time and kill your grandfather before he meets your grandmother. Your parent is never born. You're never born. So who killed your grandfather? The universe doesn't allow paradoxes. Causality must hold. Effects must follow causes. If faster than light travel creates paradoxes, then the universe must forbid faster than light travel. Not because of energy, not because of engineering, but because causality, the fundamental structure of cause and effect, breaks. The warp drive isn't impossible because we can't build it. It's impossible because the universe cannot allow it. Some physicists proposed alternatives, wormholes. Instead of traveling through space, create a shortcut through space-time, a tunnel connecting two distant points, a doorway that links Earth and Alpha Centauri directly. Step through, instant arrival. The mathematics of general relativity permits wormholes. They're called Einstein-Rosen bridges, solutions to the equations, theoretically real. But, and there's always a, but they require negative energy to stay open. Without it, they collapse instantly. The tunnel pinches shut. Space seals the wound. Suppose you found negative energy, stabilized a wormhole, opened a passage 1 meter across, connecting Earth to Alpha Centauri. The radiation inside would kill you. Wormholes concentrate all the quantum fluctuations of space-time into a tiny region. The energy density becomes astronomical. Temperature inside a stable wormhole, 10 to the power of 30 times hotter than the center of the sun, 10,000 trillion degrees. Hot enough that matter ceases to exist. Particles can't form. Reality itself unravels. And if somehow you survived the heat, gravity would destroy you. Tidal forces, the difference in gravitational pull between your head and feet. On Earth, negligible. Near a black hole, lethal. Passing through a 1 meter wormhole, tidal forces would stretch you like taffy. Spaghettification, your body elongated, atoms torn apart. Long before you reached the other side, you'd be a stream of disconnected particles. Every proposed shortcut through space-time collapses under examination. Every workaround reveals deeper impossibilities. Every door we try to open is locked not by complexity, but by the fundamental laws holding reality together. And yet we keep trying. 100 years ago, powered flight was impossible. Physics proved it. Calculations showed that machines heavier than air couldn't sustain lift. The math was clear. Then the Wright brothers flew anyway. 200 years ago, instant communication across continents was fantasy, magic, impossible. The speed of sound limited how fast information could travel. Then electromagnetic waves were discovered. Radio, telephone, internet. Now we speak to people on the other side of the planet without thinking twice. So perhaps impossible just means we haven't figured it out yet. Perhaps warp drives and wormholes seem absurd because we're missing something, a deeper understanding of physics, a phenomenon we haven't discovered, a mathematical trick we haven't learned. Perhaps. But there's another possibility, one we don't like to consider. Perhaps some things really are impossible, not temporarily, not impossible with current technology, just impossible, fundamentally, absolutely, forever. There's a child somewhere watching Star Trek for the first time, eyes wide, absorbing the idea that the stars are reachable, that humanity will slip the bonds of light speed and explore the galaxy. That child grows up, studies physics, learns mathematics, discovers Einstein's equations. works through Alcubierre's paper, calculates energy requirements, reads about negative mass and causality violations and quantum foam, and realizes it's not real. It was never real. The writers made it up because the story needed it. The science consultants did their best to make it sound plausible. But underneath the jargon, underneath the equations, underneath the hope, it's fiction. The stars remain out of reach. There's anger in that realization. The universe showed us the mathematics of the dream, but withheld the materials to build it, gave us blueprints for a house, and then revealed that the blueprint itself proves the house can't stand. It's like being shown a beautiful painting and then being told this is what could be, but isn't, but never will be. And yet, despite the anger, despite the disappointment, despite the proofs, every generation produces someone who tries again, who recalculates, who searches for loopholes, who refuses to accept that the mathematics mean what they clearly mean. Perhaps that's the definition of being human. Not intelligence, not consciousness, but the stubborn, irrational, beautiful refusal to accept no from the universe, even when no is written in equations that anyone can verify and no one can refute. Every door is closed. Bodies can't travel. Physics forbids it. Machines can only fly by no way to stop. Consciousness uploaded isn't us anymore. Identity breaks. Warp drives require impossible materials and break causality itself. Every path forward ends in a wall. Every solution reveals deeper impossibilities. So what's left? If physics won't bend, if bodies can't travel, if consciousness can't transfer, if space-time won't warp, then perhaps the cruelest barrier isn't any of these. Perhaps the real impossibility is simpler, more human, more devastating. There is something worse than death. It's knowing you'll die and no one will hear you scream. The International Space Station orbits Earth every 90 minutes. Astronauts can call home anytime. Radio signals travel at light speed, 300,000 kilometers per second. From ISS to Earth, 0.01 seconds. Instantaneous, for all practical purposes. They can speak to their families in real time, see their children's faces, hear laughter, respond immediately. I love you. I love you too. The words travel through vacuum at light speed, but the connection feels instant. On Mars, the closest we've seriously planned to send humans, communication lag is about 20 minutes. You ask a question. 20 minutes later, they receive it. They answer. 20 minutes later, you hear their response. Total 40 minutes for one exchange. Awkward, but manageable. You can't have a conversation, but you can communicate. Send updates. Share information. Coordinate. The delay is noticeable, but not crushing. Alpha Centauri, 4.24 years. Each way, you ask, how are you? The question travels at light speed for 4.24 years. In the year 2030, you send it. In 2034, they receive it. They answer, I'm fine. Their answer travels back. 4.24 years. You receive it in 2038. Total time for one exchange, 8.48 years. By the time you hear, I'm fine, you're not the same person who asked. They're not the same person who answered. 8 years have passed. You've changed. They've changed. The conversation isn't between two people. It's between two ghosts, versions of each other that no longer exist. Imagine the loneliness of that. You're on a spacecraft to Alpha Centauri. Something goes wrong. An emergency. You send a distress signal. Life support failing. Need immediate assistance. Earth receives it 4 years later. By the time they hear it, you're already dead. or you've fixed it yourself, or you've adapted, or you've given up, they send help anyway. Instructions, advice, encouragement. It arrives 4 years after they sent it, 8 years after your emergency. By then, the crisis is ancient history, forgotten, irrelevant. You're autonomous, not by choice but by physics. Earth can't help you. The light speed delay makes rescue impossible, makes guidance meaningless, makes connection theoretical. You are alone, absolutely physically, permanently alone. ISS astronauts, despite being only 400 kilometers up, barely beyond Earth's atmosphere, report psychological struggles after 6 months. Depression, anxiety, isolation. But they can see Earth from their window, can watch sunrise 16 times a day, can call home and hear their spouse's voice instantly. Mars missions would face 20-minute delays. Studies predict this alone would cause feelings of abandonment, of being cut off. The lag is short enough to remind you that Earth exists, but long enough to prevent real connection. Psychologists worry that even this mild delay could break crews, that humans aren't built for communication where every exchange requires waiting, where spontaneity dies, where conversation becomes correspondence. Alpha Centauri missions face delays 100,000 times worse. 8 years. Prisoners in solitary confinement begin hallucinating after 15 days. 2 weeks of isolation, and the mind starts breaking, creating stimuli that doesn't exist because the absence of stimulation is unbearable. How long until you forget what real-time conversation feels like? How long until you forget that other humans exist as present responsive beings rather than historical records? How long until you stop being part of Earth's civilization and become something else? At some point, impossible to define, precisely but inevitable, you cease being a crew from Earth and become a separate civilization with your own culture, your own language evolution, your own moral framework. Earth can send laws, but by the time they arrive, circumstances have changed. Earth can send advice, but it's based on situations 8 years old. Earth can send love, but the person who sent it might be dead before you receive it. You are no longer Earth's ambassador. You are a nation of 1, or a nation of 10, or 50, independent, autonomous, disconnected. There's a scenario that breaks everyone who thinks about it carefully. Your father is on Earth. You're traveling to Alpha Centauri. 5 years into the journey, Earth sends a message. Your father has died. Funeral was yesterday. We're sorry. You receive it 4 years later, 9 years after launch. But your father died 5 years into your journey, 4 years before you received the news. He's been dead for 4 years by the time you learn about it. The funeral happened 4 years ago. The grief your family experienced, the collective mourning, the shared sadness happened without you, is over now. You cry for a death that's already 4 years old. You send a message back, "I'm sorry I wasn't there. I loved him. Tell Mom I love her." It arrives 4 years later, 8 years after his death. Your mother receives your grief as archaeology. Your pain, preserved in light, arrives long after the wound has scabbed over. Every emotion you send home is history before it arrives. Now imagine this with love. You have a partner on Earth. You leave for Alpha Centauri. You're in love, committed, planning to return, though the journey is 43 years each way if you travel at 10% light speed. Year 1. You send "I love you." It arrives 5 years later, 1 year travel plus 4 years, light delay. They respond, "I love you too." You receive it year 10. But in year 6, they met someone else, moved on, married perhaps. They don't love you anymore, haven't for years. But you're still receiving their I love you messages from the past, messages that were true when sent, but are lies by the time they arrive. You continue believing they're waiting for you. Year 15, you send, I can't wait to see you. They receive it year 19. But they've been married for 13 years, have children, a life you're not part of. Their response, honest, kind, devastating, takes 4 years to reach you. You receive it year 23, 15 years after they moved on, 17 years after you sent your last expression of love. The relationship ended in year 6, but you didn't find out until year 23. For 17 years, you loved someone who didn't love you anymore, and you had no way to know. Long distance doesn't kill love. Time delay kills it. The inability to share moments, the impossibility of presence, the knowledge that by the time your partner receives your joy, your sadness, your everyday thoughts, they're experiencing something entirely different. Your lives are parallel, unsynchronized, drifting further apart every day. Philosophy, question, are you even in a relationship if your experiences never overlap, if their sadness and your comfort are separated by 8 years, if you can never be there when it matters? Communication lag doesn't just delay connection, it severs it, transforms relationship into recorded message, turns loved ones into historians studying each other's past. This has implications beyond personal relationships. A mission to Alpha Centauri cannot be controlled from Earth, cannot receive instructions, cannot be supervised, cannot be governed by Earth law in any meaningful sense. Every decision must be made autonomously. If life support fails, the crew must fix it immediately. If conflict arises, they must resolve it themselves. If someone commits a crime, they must enforce justice without legal guidance from home. Earth can send suggestions, can transmit legal frameworks, but by the time those arrive, the situation has already resolved. The precedent is set. The crew has created their own justice system, their own government, their own society. The ship becomes a nation, independent not by choice but by physics. And perhaps that's the deepest truth about interstellar travel. It's not exploration, it's exile, it's severance, it's choosing to become permanently other. The moment you leave Earth's light speed radius of real-time communication, the moment the delay becomes years instead of seconds, you cease being part of human civilization and become something new, something separate. Every person you loved becomes a ghost. Every voice you hear is historical record. Every connection transforms into archaeology. The last goodbye happens the moment you launch. Everything after is just delayed echo, messages from the past reaching toward a future that's already moved on. There's an astronaut somewhere listening to a voice, recording from his daughter. She was 5 when he left. The message is 4 years old. Daddy, when are you coming home? By the time he hears it, she's 9. Doesn't ask that question anymore. Has adapted to his absence. Perhaps resents him. Perhaps forgot what his voice sounds like. He cries listening to 5-year-old's voice, but she's not 5 anymore. She's 9. His tears are for a child who no longer exists. His guilt is for missing moments that already happened. His love arrives 4 years too late. Always. Perhaps that's the price. Not energy, not engineering, not even lifespan. The price of reaching the stars is connection. All of it. Every bond, every shared moment, every real-time presence. You can go. Physics permits it barely, but you cannot stay connected. The universe forbids that. Light speed is absolute. Time delay is non-negotiable. And maybe that's when we finally understand. The greatest barrier isn't physical, isn't biological, isn't technological. It's meaning. What's the point of reaching Alpha Centauri if you lose everything that made the journey matter? What's the point of survival if you sever every connection that made life worth living? The mathematics is clear. The physics is honest. The technology is conceivable. But the cost, the real cost, the one written in silence and delay and irreversible separation, might be higher than any human can pay. We've walked every path science offers. Physics says the energy requirements are impossible. Biology says our bodies will fail. Engineering says our machines aren't enough. Philosophy says uploaded consciousness isn't us. Relativity says warp drives break causality. And time, simple, inexorable time, says that even if we go alone. Forever alone. Alpha Centauri is there. We can see it, measure it, dream of it, but we cannot reach it. Not as we are, not as humans who need connection, meaning purpose. The question is no longer, how do we get there? The question is, if we can't get there, then what? We have asked the wrong question for 100 years. We asked, how do we reach Alpha Centauri? But we never stopped to ask, why must we reach it at all? For 100 years, we asked, how do we reach Alpha Centauri? But no one asked, why must we reach it? There's an assumption buried so deep in our thinking that we never examine it, an axiom we accept without proof. If we can see something, we must touch it. If something exists, we must go there. Distance is a challenge to overcome. Remoteness is an insult to answer. But why? Why must reaching be the goal? Why must arrival define success? You don't need to climb a mountain to appreciate its beauty. You don't need to touch the moon to feel its pull on the tides on your imagination, on the stories you tell under its light. Some of the most profound relationships humans have are with things they can never hold. Perhaps reaching isn't the same as arriving. Perhaps the value lies not in destination, but in direction, not in touching, but in looking. Consider what we actually want from Alpha Centauri. Do we want to know if life exists beyond Earth? We don't need to go there. We can detect biosignatures, chemical markers of life, in exoplanet atmospheres using telescopes, oxygen and methane together, phosphine, dimethyl sulfide, molecules that strongly suggest biological processes. The James Webb Space Telescope can detect these from 40 trillion kilometers away. Do we want to ensure human survival if Earth becomes uninhabitable? Alpha Centauri is the wrong solution. Earth has perhaps 1 to 2 billion years before the sun's increasing luminosity makes it uninhabitable. That's enough time to solve climate change, prevent asteroid impacts, develop sustainable ecosystems. And if we need to leave the solar system, we have closer options. Asteroid belt resources, Jovian moons, easier than crossing interstellar space. Do we want resources? The asteroid belt contains more metals, more rare elements, more accessible materials than we could use in 10,000 years, all within our solar system. No light-year gaps, no multi-decade journeys. Do we want knowledge about other star systems? Our telescopes improve exponentially. Each generation sees farther resolves, finer detail gathers more data. We can learn about Alpha Centauri, its composition, its planets, its potential for life, without ever leaving Earth. Strip away the romance and the practical arguments for going collapse. We don't need to go. We need it to exist. We need something beyond ourselves to look toward, but need it be reachable. Psychology offers an answer that's uncomfortable because it's true. During the Paleolithic, beyond the horizon meant survival. The tribe that stayed in one place exhausted local resources. The tribe that wondered what lay beyond the next ridge found new hunting grounds, new water sources, new opportunities. Curiosity about beyond was selected for. Built into our neurology, humans who wondered survived. Humans who didn't starved. But we no longer need what lies beyond for survival. The horizon no longer hides food or safety, yet the urge remains. Hardwired, irrational. We crave beyond, not because we need it, but because 10,000 generations of ancestors needed it, and evolution doesn't update quickly. So we project that craving onto the stars. Alpha Centauri becomes the horizon we cannot help but approach, even though nothing beyond it offers survival. The urge is evolutionary artifact, instinct divorced from necessity. We don't go to Alpha Centauri because we need to. We obsess over it because we're terrified of not having something to reach toward. Because purpose requires striving, and striving requires a target. Take away the unreachable star, and what's left? What do we reach for? The human condition includes a psychological phenomenon called the hedonic treadmill. Adaptation. We adapt to everything. Lottery winners, people who suddenly acquire millions, experience a surge of happiness. 6 months later, they return to baseline. The money no longer feels special. They've adapted. Paralysis victims, people who lose the ability to walk, experience devastating sadness. 6 months later, most return to baseline happiness. They've adapted. The treadmill never stops. Achievement brings temporary satisfaction, then fades. We recalibrate. What once seemed impossible becomes normal. The extraordinary becomes ordinary. Applied to exploration, Columbus reached the Americas, unimaginable achievement. Within 50 years, people complained about how boring the New World was. Where's the next discovery? 1969, humans walked on the moon, the pinnacle of achievement. By 1972, television networks stopped broadcasting moon landings. The public was bored. We've seen it. What's next? The pattern repeats. Humans don't need destinations. We need journey. We need the gap between where we are and where we might be, because meaning lives in that gap. Purpose lives in striving. If we reached Alpha Centauri tomorrow, if some miracle technology made it trivial, 10 years later we'd ask, what about Proxima Centauri? What about Sirius? What about Andromeda? The destination doesn't matter. The unreachability does. The gap does. The longing does. Perhaps success shouldn't be defined as arrival. Perhaps success is understanding, is transformation, is the meaning we extract from distance itself. We've already succeeded. We just haven't realized it. We cannot physically go to Alpha Centauri, but we've transformed the distance into story, into mathematics, into philosophy, into art. We've turned 4 light years of void into something meaningful, a measure of human ambition, a symbol of our limits, a reminder of both what we can imagine and what we cannot do. That transformation distance into meaning is itself an achievement, perhaps the only achievement the universe permits. Every person who has looked at Alpha Centauri and wondered, every calculation attempted, every equation solved, every spacecraft designed, every philosophical debate about consciousness and identity and the cost of reaching, all of it transforms empty space into human meaning. The gap between here and there becomes story, and story is how humans create purpose, how we find meaning in a universe that offers none. We've been asking, how do we cross the distance? When perhaps the question should be, what does the distance teach us? What it teaches is humility, scale, perspective, our place in the cosmos. It teaches us that some things remain beautiful precisely because they're unreachable, that longing can be its own fulfillment, that the journey, even when it never arrives, shapes us more than arrival ever could. There's a thought experiment in philosophy. A mountain climber spends 5 years training, conditioning their body, studying routes, preparing equipment, sacrificing relationships, career advancement, comfort, all to climb one mountain. They reach the summit, spend 5 minutes there, photograph the view, then descend. Why did they climb? For those 5 minutes? At the top, no. They climbed for the 5 years of training, for the transformation that occurred during preparation, for becoming someone capable of reaching the summit. The summit was just an excuse, a direction, a focus for the transformation. Alpha Centauri is our summit. We may never stand on its alien world, but the centuries spent trying, the mathematics developed, the technology invented, the questions asked, the dreams dreamed that changes us, makes us wiser, deeper, more aware of our place and our limits. Perhaps that's enough. Perhaps being allowed to dream of arrival without achieving it is a gift, not a tragedy. The relief in this realization is profound. You don't have to arrive to have succeeded. You don't have to touch to have connected. The longing itself, the years spent looking up, wondering, calculating, hoping that's the relationship, that's the meaning. And perhaps the universe, in its vast wisdom, knows this. Perhaps distance exists not to keep us apart, but to give us something eternal to reach toward, something that shapes us without ever being possessed. Perhaps we were never meant to arrive. We were meant to reach, and in reaching, in the eternal, impossible, beautiful act of reaching, we become fully human. But if the journey is the destination, if reaching matters more than arriving, then perhaps we've already accomplished something impossible. Perhaps we've already touched Alpha Centauri in the only way that truly matters. Plot twist: we've already reached Alpha Centauri in 1934, not with spacecraft, not with probes, with something faster, something invisible, something we sent without realizing it was a message. Radio waves, the first radio broadcasts powerful enough to escape Earth's atmosphere, began in the 1930s. Early television transmissions, propaganda broadcasts, Hitler's speeches at the 1936 Olympics transmitted with unprecedented power to reach across Germany, inadvertently reached beyond Earth. Radio waves are electromagnetic radiation. They travel at the speed of light, and unlike sound, which requires air, radio waves propagate perfectly through vacuum. 1936 plus 4.24 years equals 1940. The first human radio signals reached Alpha Centauri in 1940. We've been broadcasting ever since. Every radio station, every television show, every radar pulse, every satellite transmission, all of it radiates outward in an expanding sphere. Right now, this moment radio, waves carrying broadcasts from 1995, are washing over Alpha Centauri. 21st century transmissions are halfway there. Signals from today will arrive in 2029. If anyone is listening at Alpha Centauri, they're hearing Earth's history in sequence. A retrospective of human civilization played at light speed delay. 1940s, they heard World War II news broadcasts, artillery fire, air raid sirens, Churchill's speeches, Roosevelt's fireside chats, 1950s early television, I Love Lucy, The Twilight Zone, news of nuclear tests, 1960s moon landing broadcasts, One Small Step for Man, Vietnam War footage, The Beatles, Martin Luther King Jr.'s speeches, 1970s disco music, Nixon's resignation, the first personal computer advertisements, 1980s MTV, Cold War rhetoric, Challenger explosion coverage, 1990s grunge music, Simpsons episodes, dot-com boom commercials, 2000s 9/11 news coverage, reality television, social media's early days, 2010s streaming content, political upheaval, climate change warnings, 2020s pandemic news, AI breakthroughs, debates about the future. They're watching our species through a historical lens, seeing each event, already knowing its outcome. Every crisis preserved in electromagnetic amber, traveling through void at light speed, arriving 4 years late, but perfectly intact. What would they think of us, judging humanity through radio and television, through our entertainment, our news, our arguments, our wars? Would they see wisdom, creativity, beauty in our music and stories? Or would they see violence, tribalism, short-sighted thinking, species destroying its own habitat while broadcasting sitcoms into space? The answer is probably both, because that's what we are, contradictory, capable of profound beauty and terrible cruelty, creating art and waging war, sometimes simultaneously. But here's what matters. We didn't choose this message. We didn't carefully curate what to send. It's raw, unfiltered. Everything we are broadcast without pretense. When we intentionally sent messages like the Arecibo message in 1974 or the Voyager Golden Record in 1977, we selected carefully, put our best foot forward, showed mathematics music readings in multiple languages, represented humanity as we wished to be seen. But the accidental broadcasts, those show who we actually are. The arguments, the advertisements, the reality TV, the propaganda, the love songs and the war songs and everything between. If intelligence exists at Alpha Centauri, they know us better than we presented ourselves. They've seen the unedited version, and if they judge us harshly for that, perhaps we deserve it. Or perhaps they understand. Perhaps any species that develops radio goes through this phase, broadcasting everything, exposing themselves completely to any listener in range. Right now, that sphere of human radio broadcasts extends about 95 light years in every direction, a bubble expanding at light speed, carrying our voices into the dark. That sphere contains approximately 15,000 stars. 15,000 stellar systems have already received our messages. Some may be listening. Some may have responded their answer, traveling toward us right now, years or decades or centuries from arrival. We are not silent. We are not invisible. We're shouting into the cosmos, have been for 90 years, whether we meant to or not. In a very real sense, we've already reached thousands of stars, not with matter, with information, with light, with the electromagnetic signature of our existence. You don't need a spacecraft to travel. You just need to emit. And we've been emitting constantly since we learned to generate radio waves. The Voyager Golden Record carries this concept to its logical conclusion. Intentional message, carefully crafted. But unlike radio broadcasts that fade over distance, Voyager carries a physical record. Launched in 1977 on both Voyager 1 and Voyager 2. Two identical golden discs 12 inches across gold-plated copper. Contents selected by a committee led by Carl Sagan. What's on them? A selection of Earth's greatest hits, greetings in 55 languages, music Bach, Beethoven, Chuck Berry, Javanese gamelan, Senegalese percussion, Peruvian panpipes, natural sounds, wind, thunder, birds, whales singing, a mother's heartbeat, a kiss, laughter, images encoded in analog mathematical definitions, DNA structure, human anatomy, photos of Earth from space, children, families, cities, forests, oceans, sunset, the Great Wall of China, Golden Gate Bridge, instructions etched on the cover, a pulsar map showing Earth's location, diagrams explaining how to play the record, universal language, mathematics, and physics explaining who we are and where we're from, a message in a bottle thrown into an ocean that has no shore. Voyager 1 will never reach Alpha Centauri. It's headed in a different direction. In about 40,000 years, it will pass within 1.6 light years of the red dwarf star Gliese 445, close by cosmic standards, still separated by 10 trillion kilometers. By then, 40,000 years will have passed. 40 millennia. Every human alive today will have been dead for 38,000 years. Civilizations will have risen and collapsed. Languages evolved beyond recognition. Technologies advanced or regressed. Perhaps humanity will have reached the stars by then. Perhaps we'll be extinct. But the golden record will still be there, still playing its message, still carrying whale songs through the void, still offering proof that once briefly, improbably, a species on a small blue world looked up and tried to say hello. The longevity is staggering. The record is built to last 1 billion years. Vacuum doesn't corrode. There's no weather in space, no oxygen to rust metal, no life to decompose organic material, just cold, silence, and preservation. Long after Earth is consumed by the sun's red giant phase, 5 billion years from now, Voyager will still be drifting, still intact, still carrying our message. In a very literal sense, Voyager and its message will outlive everything, every human achievement, every building, every book, every civilization. All of it will turn to dust and vapor when the sun dies. But Voyager will remain, a cosmic tombstone, or a monument, or simply a message. We were here. We existed. We wondered about you. There's something heartbreaking about that image, and something transcendent. We cannot go to the stars ourselves, but pieces of us can go. Information, light, gold-plated records spinning through eternal night. These are the only parts of us capable of the journey. Perhaps that's the answer we've been seeking. We don't need to send humans. We need to send humanity the information that defines us, the patterns that make us unique, the signal that proves we existed. We've already done this, been doing it for 90 years. Every broadcast is a message. Every transmission is a piece of us traveling outward at light speed. We imagine first contact as meeting aliens face to face, but perhaps first contact has already happened. Perhaps right now at this moment, someone at Alpha Centauri is receiving our broadcasts from 4 years ago, listening to our music, watching our news, trying to understand who we are, and if they respond if they've been listening and decide to answer the message, is already traveling through space, taking 4.24 years to reach us. It could arrive tomorrow, or next year, or never. But the possibility exists. The conversation may have already started. We just don't know it yet. The silence we perceive might not be silence at all. It might be lag, the inevitable delay of communication at cosmic distances. They spoke. We haven't heard yet. Or we spoke. They haven't heard yet. Or most beautifully, most impossibly, we're both speaking and both listening, and the messages are passing each other in the dark. Ships in the night, on an ocean of light years, our radio waves carrying humanity outward, their radio waves carrying them inward. Both messages traveling through the same void, both carrying the same hope. You're not alone. Perhaps we've already reached Alpha Centauri in the only way that matters, not with bodies, not with machines, but with proof of our existence, with our signal, our voice, our electromagnetic whisper, saying we are here. We wonder about you. We try to speak, and if anyone is listening, if anyone has heard, then the distance between us is no longer empty. It's filled with messages, with meaning, with the light we sent and the light we hope to receive. We are not silent. We are not isolated. We are broadcasting, constantly, eternally, saying the same thing in 1,000 different ways. Hello, we exist. Can you hear us?